All right, this video is going to teach you about negative exponents and how multipliers affect exponential graphs. The first thing we'll talk about is the negative exponents part because it makes making the graphs a little bit easier to know. All right, first of all, when we talk about negative exponents, they're a lot easier to work with when you work with positive exponents. And the way you can make positive exponents is by one of two ways. You can flip the base to make the negative exponent positive, or you can, in other words, mathematically speaking, you could do the reciprocal, or you could take the whole expression itself and move it vertically in the fraction, and that also makes the negative exponent go away to make it positive. So let's look at some examples here to see what I'm talking about. Starting with this first one here, I have 2/3 to the negative first power. To make that, if you see that you have a negative exponent and I want to get rid of that negative part of it, I can flip the base or take the reciprocal and I get 3/2. Then if I have 3/2, this negative becomes positive 1. And then if I take both these things inside the base here to the first power, I just get 3/2. 3/2 is the end result of taking this 2/3 to the negative first power. If I want to take another example here of 3/4 to the negative 2 power, noticing that I have a negative exponent here, I can flip the base or take the reciprocal and get 4/3. After taking 4/3, the negative goes away and becomes positive, and then I simply just square the things that are inside here to finally get 16/9 as my final answer. Now, sometimes you might not always see a fraction. Maybe you have just a 5 to the negative 2 power. But you can think of 5 as a fraction as like 5/1. And if I flip the base, I could go 1/5 to the positive 2. Oops, sorry, 1/5 to the positive 2. And then I end up getting 1/25. So it's pretty straightforward. If you see a base like that as a fraction or no fraction, you can flip the base over with a negative exponent. We also mentioned that you can also move these things vertically. If I think of this as a fraction like negative 2 to the negative 3rd power and then making it positive, I can move this whole expression vertically down to the bottom. And by doing that, I can then have 1/2 to the positive 3rd power, which then makes 1/8. And when you take an expression and move it vertically, the negative just goes away and it becomes a positive down in the denominator, and you end up getting results like you see here. Now to go a little bit more detail with that, I'll show you the next example. So if I have 5/2 to the negative 2 power and only part of the expression has a negative exponent, let's say I move that one up to the top. This just moved up to the top, becoming then 5 joined by the 2 to the 2nd power, or 2 squared, which then this is going to equal just 4, and then I just have 5 times 4, which equals 20. But what you'll hopefully notice is that negative exponents become positive when you move them vertically in a fraction also, as opposed to just flipping the base. Now, if I have 3 to the negative 1st power, this is a negative exponent, so I want to bring that down. This expression has a negative 5 in the bottom, so I'm going to bring it to the top. And last, while I have this b to the negative 4, I'm going to bring that down. But notice when these things come back together, they're all held together by multiplication. So if I have my new answer here, I'll have, keep it in alphabetical order at least, I have my a squared still here. I've got my c to the positive 5 now in the top. And then I also have my 3 becoming a 3 to the positive 1 on the bottom, or just 3. And my b to the negative 4 becoming b to the positive 4 down in the bottom, or the denominator. This expression now explains how you can move things vertically to get positive exponents, or if it's just parts of a fraction getting moved as well. That's how negative exponents work. Now, moving on to how these things affect how multipliers change exponential graphs. We're used to seeing in the past y equals some starting value times a multiplier, right? But all we're going to do is we're going to focus on just the b value, or the multiplier. So in this case right here, if we focus on just this number, we're going to see how numbers that we put in here change how the graph's going to look. So let's start by looking at a few examples here. So if I have this example right here of y equals 1.25 to the x, this one here has a multiplier of 1.25. Now 1.25 means the multiplier is going to be increasing by 25%. So we call this an increasing graph. Increasing by 25%. Because we're saying how far above 100% is this? It's 25% above. Now, the next part is how do I graph this equation? Well, if I take anything to the 0 power, it always equals 1. So I have a dot here at 1, and then as I go to the right, 1.25 to the 1st power is going to have 1.25 as the answer. So that means it's just a little bit higher. And each time you're going to the right, you're going 25% higher, higher and higher. The graph's going to be curved, and it's going to keep going up off to the right. Not real steep, not real fast, but it's going to keep growing by 25%. And as I go to the left, it's going to keep going down a little bit each time, but it will never hit 0. So what happens then is I get down to the far right, I have this dotted line the graph gets close to, which we call an asymptote. Asymptote. A dotted line, it's a math part of a graph that the graph gets close to, but it doesn't touch in this case. So our graph here is an example of an increasing graph. It's like an airplane taking off. As it goes off to the right, it keeps getting up faster and faster as we go to the right. There are some graphs where the b value might be not larger than 1. Maybe it's less than 1, like this example right here. If I have y equals 0.9 to the x here, then what I have here is a number less than 1. And when it's less than 1 and also greater than 0, meaning that's positive, the graph's going to then come in for a landing, because as I take this to the 0 power, my graph's going to have a dot at 1, because anything to the 0 power equals 1. And if I take 0.9 to the first power, I get 0.9 again, so that's my first unit over. And as I keep going to the right, it keeps getting less and less, okay? It keeps going down by 10%. So the graph keeps getting lower and lower and lower, and over time, it keeps getting closer and closer to 0, but never touches it. Then as you go to the right, it keeps curving like the previous one, but it keeps getting higher as I go to the left. Because this graph, as I move to the right, keeps getting 10% less each time. And it keeps getting closer and closer to the x-axis, but never touches it, because if you keep taking 10% off of something, you still have something left. So again, we have a graph that looks like this. So the way you can recognize a decreasing graph, which is what this is called, this is decreasing. And you might be wondering, by decreasing by what? Well, how far is it away from 1? Well, it's 10% away. So I mean, if you thought of this as a percentage, that's 90%, which is 10 below 100. So this is decreasing by 10%. Again, it's not going down really fast, but it is going down as you move to the right. And that's what these graphs look like. All right, moving on. You might wonder, well, if it's not increasing, it's not decreasing, what about graphs that look like this? What if I have a graph that's got a b value of 1, or a multiplier of 1? Well, if I take 1 to the 0 power, I get 1. And if I take 1 to the first power, I get 1. 1 squared is still 1. Every dot that I take, any number I put in for x, 1 to that power is still going to be just 1. We call this a constant graph. The reason why it's constant is because the output is always the exact same. Okay? 1 to the x power. So constant graphs are flat. They keep going flat in both directions. Well, then you might be wondering, well, if it can't be greater than 1, less than 1, or equal to 1, then I could have it equal to 0. What is up with this? Well, if I have y equals 0 to the x power, we know that 0 to the first power is 0. But the problem is, I don't know what 0 to the 0 power is. Well, 0 powers are always determined by the number divided by itself. So if I have 0 divided by 0, that's bad because you can't divide by 0. It's undefined at 0. Then if I took 1 squared, which is 0 times 0, at 2, that's going to give you 0 also. So this graph, then, no matter what power you take 0 to the power of, will go off to the right. Now you're wondering, well, what about off to the left? If I put 0 to a negative power, like 0 to the negative 2 power, for example, that's 1 over, to make it positive, we make that negative exponent positive by moving it down to the denominator, and it becomes 1 over 0 squared. And again, 0 in the denominator is undefined, so our graph does not exist anywhere off to the left. So this graph is also flat. We could call it constant, but it's just constant from the points greater than 0. Next, what is going to happen if you chose a number that's less than 0, or negative? If I have b to some negative number. If it's b to some negative number, this is where it gets kind of interesting. If you take this to the 0 power, like we said in all these examples, it always equals 1. But if I take negative 2 to the first power, it then becomes negative 2. Well, that's down here. So at 1, I'm going to have negative 2 for my dot. And then at 3, that becomes 8. So that's 2, 3, 4, 5, 6, 7, 8, way up here. So if I take 2 squared, I'll have a 4 right here. So that's 1, 2, 3, 4. So 2 units over, I'll have 4 units up. And then 8 is way down here. This graph then follows an alternating pattern, positive, negative, as I go off to the left here, negative 2 to the negative first power, then to make it positive, negative 2 to the negative first power would then equal 1 over negative 2 to the first power, which is negative 1/2. Well, that means it's going to then go jump down here at negative 1/2, and then it goes to a 4th, then it goes to an 8th, and it keeps getting closer and closer to 0 the farther I go to the right. So you're going to have a bunch of dots that go like this, alternating going up and alternating going down. And they're dotted because our domain has to be equal increments of however we're going to go by. If we want to go by 0.5s or 0.2s or whatever you want to do, it doesn't matter, but the graph will go bouncing back and forth, positive, negative, and you get a graph that looks like this. It's just what we call a discrete graph. It does not have any kind of continuous motion or continuous dots to it. They always alternate. That's basically it. So to recap what we've talked about, negative exponents, things to think about with those, we can make them positive and easier to work with by flipping the base or taking the reciprocal, or we can move them vertically to make them positive and easier to work with. Or when we're talking about multipliers and exponential equations, if they're greater than 1, the graph's going to increase. If they're less than 1, they're going to decrease. The ones that increase are like an airplane taking off. The ones that decrease are like an airplane coming in for landing. And then we also have to think about how fast these things are going to grow or decrease. The farther they get away from 1, the faster they're going to move. So the steeper they're going to get on the right for increasing, and the steeper they're going to get on the left for decreasing as we make those graphs. Hopefully this information helps, and good luck in working with both these items.